Good day everyone. I am Dr. Jisha Mishra. Today we are going to delve into an important aspect of electronics, the common emitter configuration of transistor. Let's begin the understanding what transistors are. Transistors are tiny semiconductor devices that can amplify or switch electronic signals. In this, we learned about the common emitter configuration of transistor. Basically, the innovation of the transistor done by John Burdine, Welton Burdine and William Shockley in 1947 and 48, which led the invention of many other semiconductor devices include the integrated circuit. And in fact, due to this integrated circuit, the modern day computers and other electronic gadgets which we are using is possible, as it is well known that the bipolar junction transistor BJT is three-terminal semiconductor device. The advantage of three-terminal solid state device were immediately obvious. It is smaller and lightweight. It has no heater requirement or heater loss. It has a rugged construction. It is more efficient since less power was absorbed by the device itself and lower operating voltage where possible. It has both current and voltage gain. The transistor is a three-layer semiconductor device consisting of either two N and one P type layers of material or two P and one N type layer of material. The former is called an NPN transistor and the latter is called a PNP transistor. The figure shows the pin diagram of transistor with their symbol. The terminals have been indicated by the capital letter of E for emitter, C for collector and B for base. This figure shows the transistor. Now we talk about the internal construction of BJT. Then the emitter is heavily doped and the function of the emitter is to supply the electrons, and in fact that is why it is known as emitter. Then it is a lightly doped and the doping concentration of the collector is between emitter and the base. That means the collector is moderately doped, and if we talk about the width of this three region, then the base region is much narrower as compared to the region. So, in terms of width, the collector region is wider than the other two. Because of job of collector region is collect the electrons which is supplied by the emitter, and in fact that is why it is known as a collector. Now depending on the biasing, the BJT can be operated in three regions. First is active mode. It is also called as a amplification mode. Second one is saturation mode and the third one is cutoff mode. The DC biasing is necessary to establish the proper region of operations for AC amplification. The emitter layer is heavily doped with the base and collector only lightly doped. The lower doping levels decreases the conductivity, increase the resistance of the material by limiting the number of free carriers. The below figure shows type of transistor in which figure A is the PNP type and the figure B is NPN type. The operation of the NPN transistor is exactly the same in the role of played by the electrons and holes are interchanged. Figure 1 A figure shows the PNP and figure B shows the NPN. As shown in the below figure, the PNP transistor has been redrawn without the base of collector bias. Let us now remove base to emitter bias of the PNP transistor as shown in the figure. The depletion region has been increased in width due to the applied bias. The flow of majority carriers is 0, resulting in 1A minority carriers flow. Now consider one PN junction of a transistor is reverse biased, whereas the other is forward biased. Common emitter configuration where both biasing potential have been applied to a PNP transistor with the resulting majority and minority carriers flow indicated as shown in figure. In common emitter configuration, base is the input terminal, collector is the output terminal and emitter is the common terminal for both input and output. That means the base terminal and common emitter terminal are known as input terminals, whereas collector terminal and common emitter terminal are known as output terminals. In common emitter configuration, the emitter terminal is grounded, so the common emitter configuration is also known as grounded emitter configuration. Sometimes common emitter configuration is also referred to as CE configuration, common emitter configuration or CE amplifier. The common emitter configuration is the most widely used transistor configuration. The width of the depletion region indicating clearly which junction is forward biased and which junction is reverse biased. A large number of majority carriers will diffuse across the forward biased PN junction into the N type material. Since the sandwiched N type material is very thin and has a lower conductivity, a very small number of these carriers will be take the path of higher resistance to the base terminal. The magnitude of the base current is typically on the other of microamperes and compared to milliampere for the emitter and collector currents. The large number of these majority carriers will diffuse across the reverse based junction into the P type material connected to the collector terminals. The reason of the relative which is majority carriers can across the reverse biased junction is easily understood if we consider that for the reverse bias diode, the injected majority carriers will appear as minority carrier in the n-type material. Applying Kirchhoff current law to the transistor, if it were a single node, we obtain IE equal to IC plus IB and find that the emitter current is the sum of collector and the base current. The collector current, however, comprises two components, the majority and the minority carriers. The minority current component is called the leakage current and the given the symbol is ICO, IC current with emitter terminals open. The collector current therefore is determined in total by IC equal to IC majority plus ICO minority. In this figure, show the notation and symbol of transistor used with the common emitter configuration. The common emitter type is most frequently encountered transistor configuration. Figure, notation and symbol used with the common emitter configuration. A is NPN transistor, the second one is PNP transistor. In common emitter presented is CE configuration, input current or base current is denoted by IB and output current or collector current is denoted by IC. The common emitter amplifier has medium input and the output impedance levels. So, the current gain and the voltage gain of the common emitter amplifier is medium, however, the power gain is high. An NPN transistor configuration. We know that the transistor is a current operated device beta model and that a large current IC flow freely through the device between the collector and the emitter terminals. When the transistor is switched fully on, however, this only happens when a small biasing current IB is following into the base terminal of the transistor and the same time, thus allowing the base to act as the short of current control input. The transistor current in an NPN transistor is the ratio of these two current IC by IB called the DC current gain of the device and is given the symbol of HFE or nowadays beta. The value of beta can be large up to 200 for standard transistors and it is the large ratio between IC and IB that makes the NPN transistor a useful amplifying device when used in its active region, as IP provides the input and IC provides the output. Note the beta has no unit as it is a ratio. As the emitter current LE is the product of a very small base current plus a very large collector current, the value of alpha is very close to unity and for a typical low power signal transistor, this value range from about 0.950 to 0.999. The emitter collector and base current are shown in their actual conventional current direction. Even through the transistor configuration has changed, the current relations developed earlier for the common base configuration are still applicable. For the common emitter configuration, The output characteristics are a plot of the output current IC versus output voltage VCE for a range of values of input current IB. The output characteristics are a plot of the input current IB versus the input voltage VBE for a range of value of output voltage VCE as shown in figure. The curves of IB are not as horizontal as those obtained for IE in the common base configuration, indicating that the collector to emitter voltage will influence the magnitude of the collector current. Common emitter characteristic for input characteristic: change between the base emitter voltage to change in the current base is input characteristics. Output characteristics presents the change between the voltage collector to change in the collector current. For the transfer characteristics present that change between the current collector to change in base current. The below figure shows the output and input characteristics of a silicon transistor in the common emitter configuration. A output characteristics, B is a input characteristics. So that the figure 1 is presents the output characteristics and the figure B is presents the input characteristics. Now we are talking about the input characteristics. The input characteristics describe the relationship between input current or base current IB and the input voltage or base emitter voltage VBE. The input current or base current IB is taken along y axis vertical line and the input voltage VBE is taken along x axis horizontal line. The second point is to determine the input characteristics, the output voltage VCE is kept constant at 0 volt and the input voltage VBE is increased from 0 volt to different voltage level. For each voltage level of input voltage VBE, the corresponding input voltage IB is recorded. The output voltage VCE is increased from 0 volt to certain voltage level, let say 10 volt, and the output voltage VCE is kept constant at 10 volts. While increasing the output voltage VCE, the input voltage VBE is kept constant at 0 volts. After we kept the output voltage VCE constant at 10 volts. The input voltage VBE is increased from 0 volt to different voltage levels. For each voltage level of input voltage VBE, the corresponding input current IB is recorded. When output voltage VCE is at 0 volt and emitter base junction to forward biased by input voltage VBE, the emitter base junction act like normal PN junction diode. So, the input characteristics of the common emitter configuration is same the characteristics of the normal PN junction diode. Now, the cut of voltage is silicon transistor is 0.7 volt and the germanium transistor is 0.3 volts. In input characteristic, the common emitter CE configuration, the input current IB is very small as compared to input current IE. In common base CB configuration, the input current in C configuration is measured in microampere mu A, whereas the input current in CB configuration is measured in milliampere MA. From the above characteristic, we can see that for higher fixed value of output, voltage VCE, the curve shifts to the right side. This is because for higher fixed value of output voltage, the cut in the voltage increased above 0.7 volts. Now, output characteristics. The output characteristics describe the relationship between output current IC and output voltage VCE. The output current or collector current IC is taken along y axis vertical line and the output voltage VCE is taken along x axis horizontal line. To determine the output characteristics, the input current or base current IB is kept constant at 0 mu A and the output voltage VCE is increased from 0 volt to different voltage levels. For each level of output voltage, the corresponding output current IC is recorded. A curve is then drawn between output current IC and output voltage VCE at constant input current IB 0 mu A. When the base current of input current IB equal to 0 mu A, the transistor operates in the cut-off region. In this region, both junctions are reverse biased. Next, the input current IB is increased from 0 mu A to 20 mu A by adjusting the input voltage VBE. The input current IB is kept constant at 20 mu A. We kept that input current IB constant at 20 mu A. The output voltage VCE is increased from 0 volt to different voltage levels. For each voltage level of output voltage VCE, the corresponding output current IC is recorded. The curve is then drawn between output current IC and the output voltage VCE at the constant input current IB 20 mu A. The region is known as active region of a transistor. In this region, emitter base junction is forward biased and the collector base junction is reverse biased. When the base current or input current IB equal to 0 mu A, the transistor operate in the cut-off region. In the region, both functions are reverse bias. When output voltage VCE is reduced to a small value 0.2 volt, the collector base junction becomes forward biased. This because the output voltage VCE has less effect on collector base junction than input voltage VBE. As we know that the emitter base junction is already forward biased, therefore, when both the junctions are forward biased, then transistor operates in the saturation region. In this region, a small increase in output voltage VCE will rapidly increases the output current IC. The active region for the common emitter configuration is that portion of the upper right quadrant that has the greatest linearity, that is that region in which the curve for IB are nearly slight and the equally spaced. The region exists to the right of the vertical dashed line is VCE and the above curve for IB equal to 0. The region to the left of VCE is called the saturation region. In the active region for a common emitter amplifier, the base emitter junction is forward biased, whereas the collector base junction is reverse biased. The active region of the common emitter configuration can be employed for voltage, current or power amplification. The cutoff region for the common emitter configuration is not as well defined as for the common base configuration. IC is not equal to 0 when IB is 0. The reason for this difference in characteristics can be derived from the equation IC is equals to alpha IE plus ICBO, also known as IC is equals to alpha IC plus IB plus ICBO. Now, IC is equals to alpha IB by 1 minus alpha plus ICBO by 1 minus alpha. For the figure reference, the collector current defined by the condition I be equal to 0 mu A will be assigned the notation indicated by the following equation. The equation is given there. ICEO equal to ICBO upon 1 minus alpha. Current gain alpha. The current gain of the transistor in CE common emitter configuration is defined as the ratio of output current or collector current IC to the input current or base current IB. The equation is alpha equal to IC upon IB. The current gain of the transistor in CE configuration is high. Therefore, the transistor of CV configuration is used for amplifying the current. Beta DC mode. In the DC mode of the level of IC and IB related by a quantity called beta and defined by the following equation. Beta DC equal to IC by IB, where IC and IB are determined at a particular operating point on the characteristics. For practical devices, the level of beta typically range from about 50 to over 400, with most in the mid range. As for alpha, the parameters beta reveals the relative magnitude of one current with respect to the other. For a device with a beta of 200, the collector current is 200 times the magnitude of the base current. Dynamic input resistance. Dynamic input resistance is defined as the ratio of change in input voltage or base voltage VBE to the corresponding change input current or base current IB with the output voltage or collector voltage VCE kept in the constant. Now, the dynamic input resistance equal to VBE upon IB, VC is constant. In CE configuration, two input resistance is very low. Dynamic output resistance. Dynamic output resistance is defined as the ratio of change in output voltage or collector voltage VCE to the corresponding change in the output current or collector current IC with the input current or base current IB kept the constant. RO is equals to VCE upon IC. C is a configuration the output resistance is high and IB is constant. AC mode. For AC saturation and AC beta is defined as a follow. Beta AC equal to change between IC upon change between IB, BC is constant. The formal names of beta AC is common emitter forward common amplification factor. A relationship can be developed between beta and alpha using the base relationship introduced thus for alpha and beta relationship in NPN transistor defined here. For DC current claim equal to output current divided by input current IC equal to IB. After that we use KCL law and resultant is alpha divided by 1 minus alpha. Beta equals to alpha divided by 1 minus alpha, and other hand alpha is equals to beta divided by beta plus 1. if alpha is equals to 0.99, beta equals to 0.99 divided by 0.011. So, the result is 99. The value of a beta vary from about 20 for high current power transistor to well over 1000 for high frequency low power type bipolar transistor. The value of beta for most standard NPN transistor can be found in the manufacturer's data sheets, but generally range between 50 to 200. Some key features of common emitter configuration: input impedance is medium, output impedance is high, phase angle is 180, voltage gain is medium, current gain is medium, power gain is very high. In this slide, we complete common emitter configuration of transistor. In the next session, we discuss the example of common emitter configuration and the some definition of BJT and other perspectives. Thank you.